let f of x be equal to the rational function x minus 2 over x plus 2. We want to show three things. First, f is 1 to 1. Then we want to sketch f inverse. Then I want to find the formula for f inverse and verify. Now, inverse functions. What are we trying to do here? So, we have our function f. Suppose it sends x to y. What we're trying to do is, I want a function g that undoes the operation of f. So g is going to take y and return x. Now, if that g exists, we're going to call that f inverse. And so, by definition, we're going to have g of y is equal to x, or f inverse of y equals x. So far, just a language trick. Now, using that language trick, we get two equations. First, we'll have f inverse of f of x equals x. So what's happening here? Well, if f of x is equal to y, then I hit that with f inverse. F inverse of y just returns me back to x. So, f inverse of f of x equals x. How about the other way around? If I take f inverse of y, that's going to give me x. Then I hit that with f, and then I get y back. So, f of f inverse of y is going to be equal to y. Now, if I have an inverse function, that's a good way to check it. You can use either one of those equations. What else do we have? Now, let's think of functions as order pairs. So I can think of f as being the order pairs x comma y. That's how we're going to get our graph. For f inverse, what are we doing? We're switching x and y. So f inverse takes y, returns x. So if I have a point xy on my graph of f, a point on the graph of f inverse is going to be y comma x. So that's going to give me two things. First off, if f inverse exists, then I get the graph of f inverse of x by just flipping the graph of f in the line y equals x. Then, this is the big one, we'll have a check for whether f inverse exists or not. Now, if I want an f inverse, it's got to be a function. So we can't have points which have more than one value. So the idea is we have to satisfy the vertical line test. Well, when I switch x and y, the vertical line test for f inverse becomes the horizontal line test for f. So that's our check whether f inverse exists or not. Okay, we use the horizontal line test. Now the horizontal line test is the same as saying f is 1 to 1. That just means if I have f of x, okay, some other point f of y on the same horizontal line, then if they're equal, they have to have x equals y. We can only have that horizontal line cutting the graph of f in one spot. Okay, let's move on to the three items we're looking for. First, is f 1 to 1? First way we can get this, we just graph f, apply the horizontal line test. Now, here's my graph of f, okay? How do I get it? You can either go to computer or graphing calculator, or you just run through the steps for graphing a rational function. So, in this case, when I take a look at this, we have x minus 2 over x plus 2. Two items I can get. Okay, the zeros of f are going to be where the numerator is equal to 0. So it's going to be where x is equal to 2. So that's going to give me the point f of 2 equals 0. So right there. Then, if I take a look at the denominator, okay, our function is going to be defined everywhere except at x equal to minus 2, and then we're dividing by 0. At that point, we're going to have a vertical asymptote. So at minus 2, I have a vertical asymptote. What else do I have? I can get another point. If I put 0 in here, we're going to get minus 2 over 2 is a minus 1. So it gives me this point here. Then what else can I do? We also have the end behavior of the graph. So it's going to be this horizontal asymptote at y equals 1. If you note, okay, we have x minus 2 over x plus 2. We only worry about the lead terms, so I can forget about the 2's. It's going to give me x over x. And as we go out to plus or minus infinity, that's just going to go to 1. So as we go off to the far right or the far left, our graph has to go to 1. Now, so we have point, point, asymptote, asymptote. How do I get the rest? Next step I can do, we can break up, okay, the real line into 3 regions. So the only way my graph can go from positive to negative or negative to positive is if it goes through a 0 or an asymptote. So we're going to have 2 breaks in the real numbers, at our vertical asymptote of -2 and at our 0 of 2. I only need to check 1 point in each region to get the sign for the entire region. So we already know the middle region. We know that at 0, I get a -1. So we're always going to be negative here. Then if I want to get the sign on these other 2 regions, we just check 1 point. That 1 point that we get will be good because then I can use it for a reference point when I graph. So I'll do 3 and -3. So if we put them into the equation, we'll get a 1/5 and a 5. So we're going to be positive on both of these regions, and then we can plot our points. Okay, so for 3, we're going to have a point around there. For -3, we have a point up here. Then you just connect things. So we have a point here. We're positive in this region, so this has to go to +infinity at this asymptote. Then as I come down, I have to go to the horizontal asymptote at 1. For this piece, we connect our dots. Okay, on this end, I have a horizontal asymptote at 1, so we bring it up. And then on this side, we're going to have negative, so I have to go down to the vertical asymptote on this side to -infinity. So there's my graph. And then you note, if you take any horizontal line, it's going to hit the graph exactly once if it does at all. So it won't hit anything on the graph if you're at y = 1. So by the picture, it satisfies the horizontal line test. So f is 1 to 1. Now, you could do this computationally also, so you don't even need to go near the graph. I could just set f of x equal to an f of y, and then show that x has to be equal to y. So that says on any horizontal line, we can only hit the graph at most once. So I set f of x equal to f of y, so we write out our rational function with x, and then with y, and then we solve. So I just clear the denominators out. Okay, then we're going to expand everything. Then when I start simplifying, I get down to a 4x equals 4y, and so x is going to have to be equal to y if this occurs. So that's going to be the formal definition of 1 to 1. So you have 2 ways to get 1 to 1. Either draw the picture or use the formal definition of 1 to 1. Next step, let's find the graph of f inverse. Now, on my previous board, we collected some data about the graph of f. We can use that here. So we have 4 points, 2 asymptotes. Our points are 0, -1, 2, 0, 3, 1/5, -3, 5. Horizontal asymptote is going to be y = 1. Vertical asymptote at x equals -2. If I want to go from f to f inverse, we're just taking xy going to yx. Then horizontal asymptotes go to vertical asymptotes. Vertical asymptotes go to horizontal asymptotes. So the data that we get for f inverse is going to be 4 points, -1, 0, 0, 2, 1/5, 3, 5, -3. We're going to have a vertical asymptote at x equals 1, horizontal asymptote at y equals -2. So we put our asymptotes in. So that's x equals 1, y equals -2. Then we have 4 points. So there's -1, 0, 0, 2. Okay, then we have 1/5 up 3. And then our other point over 5 down -3. Okay, all we need to do now, take the original graph, flip in the line y equals x. So normally you have to look at your graph kind of on its side, but here we just see we have this one bowl connected to the asymptotes, flipping to a bowl over here connected to the asymptotes. So we just have to connect the dots. So that's going to be my graph of f inverse. Now, let's find the formula for f inverse. How do I proceed? We start by writing y equals f of x. So I'll have y equals x minus 2 over x plus 2. We switch x and y. That's going to give me x equals y minus 2 over y plus 2. And then I just solve for y. So we push the y plus 2 to the other side. I expand. And then here we want to isolate y. So I'm going to put all the y stuff on one side, all the non-y stuff on the other. So 2x goes over here. The y comes to this side. We can factor out an x minus 1. So y is now by itself. So I divide by x minus 1. We get y equals minus 2, 1 plus x over x minus 1. To clean it up, I'll multiply by a minus 1 over itself. That's just going to take out the minus sign. So we'll have f inverse of x, okay, equals y, equals 2 times 1 plus x over 1 minus x. If I take a look at my graph, okay, note this is saying I have a 0 at minus 1 and a vertical asymptote at x equals 1. So 0 at minus 1, vertical asymptote at x equals 1. So at least that checks out. Finally, let's verify using one of our formulas from board 1. So we'll use f inverse of f of x equals x. Now, what are we going to do here? First, we suppose that we have f inverse of box. So that's going to mean f inverse of box equals 2, 1 plus box over 1 minus box. We take our complicated expression for f of x, just stick it in the box. So we'll have 2 times 1 plus x minus 2 over x plus 2 over 1 minus x minus 2 over x plus 2. We're going to clear out the denominators by multiplying by x plus 2 over itself. In the numerator, okay, we'll have our 2. This goes to the inside. We have an x plus 2 plus x minus 2. That's going to collapse to a 2x, but we multiply by 2, so I get 4x. Then in the denominator, we'll have x plus 2 minus x minus 2 in parentheses. So we want to make sure we push the minus sign in correctly. Then the x's are going to go away, and I'm left with a 2 minus a minus 2, which gives me a 4. So we have 4x over 4, and that means we have an x, so our formula checks out. Okay, I'll leave it to you as an exercise to check the other formula.